Welcome to our fourth time together this week. This begins our discussion around statistical testing. We've spent 3 sessions talking about how to create variables, how to identify the levels of measurement in the variables and correct them in SPSS. And now we're going to use all of that work to help us statistically test the difference between groups. So I hope you're feeling the power of statistics mounting. As I said earlier in our sessions together in the course, statistics are very powerful because they help us reduce large amounts of data into easily interpretable and actionable results, numbers, and findings. So let's see how that plays out this week. We talked at length about how exploring data is the key foundation that we must do to understand our variables so that we can design statistical tests to help us address the variables we're dealing with as well as the broader question and problem statement that we've created. And it's only then that our analysis can be effective and powerful and link back to the problems that we've described. So let's talk about how to test differences in proportions. So we're going to divide this talk into large groups and small groups. How do we test differences in proportions when those those groups are large or small in size? So we'll start with the large one. This, by and large, are certainly the most common. So chi-square is a non-parametric test. It doesn't assume a normal distribution of data, but it is used for large sample sizes. And it also goes by the name of Pearson's chi-square test of independence. And I want to unpack that a little bit and show you a common tool in epidemiology and statistics that is the basis for this test, because this concept really is a building block that you'll come back to repeatedly in your statistical life. And that's a 2x2 table. So I've taken an example here of 2 different groups, faculty and students. So these are 2 different groups based on their academic activities. And we've also looked at stress level here on the left in 2 different groups of high stress level and low stress level. And we're assuming that there is some sort of a test or an instrument for measuring stress, and we're able to take the findings from that instrument and categorize people based on a high or low stress level. So let's say, for example, we have 100 faculty and 100 students. We test them all, and we find that 50 faculty have high stress levels, 50 have low, and the same for the students. So those red numbers are the basis of the 2x2 table. You can see for the stress level high, that category, we have 2 results for faculty and students, and the same for low. We have a result for faculty and for students. So that is 2 categories across the top and 2 categories across the side. That's the basis for the chi-square test. And each of the rows and each of the columns has a total as well. And the black numbers here are called the marginals. So that's the sum of each column and each row. So this is a full 2x2 table, but the 2x2 names comes from these 2 categories, these 2 categories. So let's say, for example, we've tested those 100 faculty and those 100 students, and we have 5 faculty with high stress levels and 95 with low. When we test the students, we have 75 with high stress levels and 25 with low. So then our question becomes, is that difference based on chance alone or fluke, or can we statistically conclude that the proportion of stress in the faculty and the students, the proportion reporting high stress in those groups, are different? So that's what the chi-square test is designed to do. Essentially tell you, are these two groups different? And another way of saying that is, are the variables independent? So is the outcome the same for the two levels of the predictor? Let's look back at our 2x2 table to help make that a bit more concrete. So when we look at the faculty and the students, those are two categories of academic activity. So the question of the chi-square test is there a difference in this high stress level between faculty and students? So is this 5 versus 75, is that a real difference statistically? Or can we not conclude that these groups, the groups of faculty and students, differ on their level of stress? So here you see, are these two variables independent? So is stress level and academic activity, are those variables independent? Do the proportions of students with high stress and faculty with high stress differ or not? So as with every statistical test, there are assumptions that go behind the test. So for the chi-square test of independence, it's assumed that in each of those squares of the 2x2 table, you have a large group, and that's defined as 5 or more observations, with none of the boxes having 0 in them. It's also assumed that the observations are independent, so the faculty and the student stress levels are unrelated to each other. And if those students and those faculty are in the same courses together, that assumption may not hold true because they share that coursework in common. And so that could potentially compromise or limit our use of the chi-square test. But if these are faculty and students who don't share academic work or relationship together, then the observations for their stress levels would in fact be independent. It assumes that we have a random sample that we have selected from the population, and the total probability of an event is 1. So if we look at the probability assumption here in this 2x2 table, the total probability that someone will have a high stress level, so you'll see here I had incorrectly not adjusted the row totals after modifying this example. So here in this 2x2 table, these row totals are now correct for our case example. So let's go back to our chi-square test, where we're looking at the null hypothesis. So the null hypothesis for the chi-square test is that the row variable is independent of the column variable. So what that practically means is that the two groups are different. So in our case example, it's saying that the two groups are different for their stress levels. Or stated another way, looking at our 2x2 table, the null hypothesis is that the academic activity of faculty and student is independent of the stress level, and the stress level is independent of the academic activity. So that's the null hypothesis, that these two rows and columns are independent of each other. And we can see from these hypothetical data that it appears that there actually is a relationship between faculty and student academic activity and stress level. It appears from this 2x2 table that faculty have a much lower level of stress than students. And you can use the chi-square test to formally test if that is true or not. So let's go to SPSS and create a variable where we group the regions into further categories. So let's go to recode into different variables. And we're going to scroll down to what we've already selected, and we've created regions. So let's select that variable, region, from the Health and Human Services map, and we're going to make a new one called toRegion. I've already done that, so of course testing it. So let's reset and see how we would do that from scratch. So let's scroll down and we'll select our regions from Health and Human Services, and then we're going to call this new variable toRegion. And what I'd like to do now is apply some of the tools that we used before. We'll go back to the regions map that we had, or the list that you've created, and I want to make a contiguous versus outlying United States dichotomy now. So if you look back on the regions, region 1 can be converted into contiguous United States. So it's part of the 48 major U.S. states. That was New England. And then if we have the starting at region 3 all the way through region 10 is also in the contiguous United States. So we'll add that. Now region 2 was the outlying peripheral islands and territories. So islands will code into category 2. It's outside the contiguous United States. And then also category number 11 of Alaska, I'm sorry, the original region number 11 of Alaska and Hawaii, we're going to code as 2. So that's going to be outlying United States. So we'll say continue. We'll say yes, in fact, we do want to create those 2 regions. And you can see here in SPSS it's told you it has created them. So let's flip over to our variable view, select this 2 regions. It's numeric, it's given at 2 decimal places, which again you don't need, so you can take those away. And let's label it. This, we'll call it contiguous versus outlying US, and then we'll label it. So we said value of 1 was going to be contiguous US. We'll add that, and 2 is outlying. All right, so now let's see how we can run a chi-square. As in much of SPSS, there are multiple ways to do this, so I'll show you several as we go through this. The first one is we're going to go to descriptive statistics and back to, tables, and we'll go to custom tables. And again, it gives us the warning, you need to know how your variables are defined. And in this table, let's pick our contiguous versus the outlying United States. And we'll make that a row. I'll take away an old variable that I had in here from before. And now we want to compare it to our discharge instructions that we split into our 2 categories. Now the test statistics we want is the test of independence, the chi-square, with an alpha set at 0.05, which is the standard. So let's go ahead and run this and see what it tells us. So interestingly, when we get the breakdown of observations, you can see you have very many facilities here in the contiguous United States, 793 and 980, but only very few in the outlying United States, 3 and 4 respectively. So we've run the chi-square test to test if the 2 groups are independent, or if the outcome variable is independent of the predictor variable. So under Analyze, we go to Tables, Custom Tables. All right, we know we have our 2 variables selected, talked about. And you see here the p-value for chi-square is 0.921, meaning we can't conclude that the difference in discharge instructions is different by the location within the United States. But we'll take a look at footnote A when we come back in our second part.